In this lesson, we will study about breadth first search traversal, or in short BFS traversal of graphs. And in the later part of this video, we will also see the implementation of BFS algorithm using C++, Java and Python. So first, let's understand what is meant by this term traversal. So traversal means visiting every vertex. A graph is composed of vertices and edges. So we have to visit each vertex and edge exactly once. So we will never go to a vertex which is already visited. And the order in which the vertices are visited is important, and that will depend on the algorithm that we are using or the problem that we are solving. The order in which the vertices are visited in BFS is not the same as DFS. DFS is another graph traversal algorithm. It's called depth first search, and here it's breadth first search. Breadth means if you start from here, you go to all the neighbors. Depth means you go as deep as possible, and then when you are stuck or reach a already visited node, you come back. This will be more natural way of exploring, but breadth first search is also very widely used. Both are equally important. And during a traversal, it is important to keep track of visited vertices. This will be common to all the traversals that we do. So if you don't keep track of visited nodes, you may never complete. You may again go to a node which was already visited, but you are not keeping track of that. So that makes sense to keep track of which nodes are visited. And the two most common ways of traversal are BFS and DFS. In this lesson, we will study about the first one, that is BFS. So BFS means breadth first search, and as the name says, we traverse the graph breadth-wise. First move horizontally and visit all the nodes of the current layer, and then move to the next layer. So there is a notion of starting node in the traversals. We generally denote it with small s. In code, it will be some value like 0, 1, 2 each node. So let's say this is node 0, 1, 2, 3, 4. And we start from here. This is our starting node. So first we visit this. So we will keep at level 0. That is, this vertex is at a distance of 0 from the source or starting vertex. Next, we will go to all the nodes which are at a distance of 1 unit from this starting vertex, and we will call that all those vertices to lie in level 1, since they are at a distance of 1 from this. Here we are not talking about weighted graph. You can think of it as unweighted graph, and we are calculating distance in terms of number of edges. So these are the immediate neighbors of this starting vertex, which is at 0 level. So each of them are at 1 unit distance from this. This is 1, this is 1. So all of them are at level 1. What is the distance of these three? It's the neighbor of 1, which is itself a neighbor of 0. It's a distance of 2. So 3 and 4 are at level 2. Within a level, the order in which they are visited may vary depending on the order in which you have put them in the adjacency list. So just for recap, this is the adjacency list of this one. So this vertex is 0. So the neighbors of 0 are 1 and 3. Neighbor of 1 is just 2. So this will be the 1. This is 1, this is 2. Sorry, 3. So this is 3, and neighbors of 1 is just 2, this is 2, and neighbors of 3 are 2 and 4, so this is 4. So this is the adjacency list. So the order in which you insert them, let's say 3 comes before 1, then you will visit 3 first. So within a level, that ordering may vary, but first you will visit all the nodes at level 0, that is 0 itself, then 1 and 2, these are at level 1, level 0, level 1, then you will visit level 3 and 4. Now the question is how we can achieve this kind of result. So you might have already seen level order traversal of trees. But the here only thing is that there can be multiple paths to a given node, unlike the tree where we have a unique path from source or root to any node. Here you can see that we can reach 4 from 0 to 4 and also from 0, 1, 4. So this is the difference from tree. So now let's see how we can achieve this. Let's see the BFS algorithm. So G is a graph and S is the starting node. In this case, this one, 0. So what we do, first we enqueue it into a queue. So we keep track of a queue and then we mark it as visited. So as soon as we push something into the queue, we mark it as visited, and we will see why we need to mark it as visited right after its enqueuing and why not after dequeuing. And once we have enqueued it, the queue is not empty. We have added the source into it, that is node 0. And if you remember correctly, this was 1, this was 3, this was 4, and this was 2. So 0 is in the queue. Then we dequeue it from the queue, and after dequeuing we look at all its neighbors. So what are its neighbors? 1 and 3. 2 neighbors are there. So we put all the neighbors into the queue if they are not visited. If they are visited, we will not enqueue them. So because maybe that we reach the second level, we are trying to visit the second level, but there is an edge going from this to maybe source or some earlier layer. So that will already be visited. So we will not enqueue them again. So this is very simple. Enqueue the source into the queue, and while the queue is not empty, keep doing this. You dequeue it, you look at all the neighbors of the dequeued node, and if that is not visited, enqueue it, and whenever you enqueue, you mark it as visited. So let's run through an example on a sample graph. So here we have also written the adjacency list representation. So first queue is empty, we enqueue the source, so 0 is here. Now while and also keep track of visited. So visited will have 5 values, 1 for each node, 0, 1, 2, 3, 4. So initially everything is false, none of them are visited. So we have enqueued 0 into the queue, so we mark 0 as visited, that is true. Let me write here, this is visited. Next, while queue is not empty, so this is queue. What we do, v equal to queue dot pop, or we will have different functions in different languages. In C++ we will write front and then we will pop. Pop does not return the front element. So let's say pop returns front element. So we have popped it and also returned it. So now queue becomes empty. But this loop, the body of this loop will be rechecked this condition only after reaching the end. So here we have popped it, so queue is this one, empty. Then we look at all neighbors of V which are not visited. So neighbors of V is here nothing but 0. Neighbors of 0 are 1 and 3. We see here 1 is visited, no. 3 is visited, no. So enqueue them into the queue. So now queue becomes 3 and 1. So once we pop it, we can print it. We will mark it as traversed. So we can print, let's say we are printing here after this, after dequeuing. So we print 0. Next 3 and 1 are in the queue. So once we enqueue it, we mark them as visited. So 1 becomes true, 3 becomes true. Now this body will end here and again go back and check if queue is empty or not. Queue is not empty, it has 2 elements. So it will dequeue it. The first one, let's say we enqueued 3 first before 1. As I said, we can, this order may vary depending on how you have built the adjacency list. So we will pop 3. So 3 is popped and we look at its neighbors, and we also print it after popping. The neighbors of 3 are 2 and 4. So we check 2 is visited, no, so enqueue it into the queue. So queue becomes 3 is popped, 1. So in queue we remove from beginning and insert in the end. So 3 was inserted first, so it will be removed. So anything we insert will be inserted after 1. So that's how this is printed in level wise. That is, first level we have inserted at the same time all of these values. So the values which are enqueued first will be dequeued first, because queue follows first in first out. So that's very important for this level order traversal. So now 1 is remaining, but we look at neighbors of 3, which is 2 and 4. Both are unvisited, so we insert 2 and 4 into it, mark them as visited, and we have printed 3. Now again this loop body has ended. It will again check if it's empty, no. So next we will pop 1 and print it, check the neighbors of 1, which is 2, but 2 is already visited, you can see here, so we will not reinsert it. Next again check if queue is empty, no, so we pop the front of the queue, that is 2, print it and look at the neighbors of 2. 2 does not have any neighbor, so continue. Again queue is not empty, so we pop 4 and print it, look at the neighbors of 4. 4 does not have any neighbor, so again we go back and check if queue is empty or not. Now queue is empty, it does not have anything, so we return. So this is the order in which it was printed. So let's verify 0. 0 is at the 0th level. Next we have 3 and 1. 3 and 1 are at immediate neighbors of 0, that is at a distance of 1 or at level 1. So they are printed. And then we print 4 and 2, which are at the next level, that is at a distance of 2 from the source. So let's write the code for this in C++, Java and Python. In this video, I will give the complete implementation of graph and how to add edges to the graph, how to represent it in adjacency list form. So since this is one of the very first lectures of graph, this is the third lecture. So in the further lessons, I will start from the class that is implemented already, and we will focus on the main algorithm. So let's pay attention to this lecture, since here we will do complete implementation. So we will need a queue. So in C++, we need to include queue from STL. You can use other linear containers as well. You can use even list. You pop from the beginning and you insert in the end. So that way you can use list also. But let's use queue if it's available in C++. And now let's define the graph class. So it will have number of vertices. So let's call it m_v. So m_ I am using for class member variables. And then we will have the adjacency list. So we can use that as vector of int and then define a constructor here, or let's write it in a small. So this outer list will be of size v. I think this constructor is done. Let's define the next method, which is how to add edge into a graph. So we will start with an empty graph, then we will keep adding the different edges, and we will follow this same graph that we saw here. And if it's not directed, then it will automatically be captured in the adjacency list. So if 1 is in the adjacency list of 0, 0 will also be there in the 1. So it will be two-way. Both are neighbors of each other. So that will not make any difference. In the code, you just have to go to if you want to visit all the neighbors of 3, you will go here and look at this list. So that does not make a difference. Only difference will be in the add edge function, which we will implement just now. So let's say we want to add an edge between u and v. So in directed case, it will be like this. So in adjacency list of u, v will be inserted. And if it's undirected, that is uv, then we will do it twice. In the adjacency list of u, insert v, and in v, insert u. So this one line change will be there in the add edge function. Other than that, there should not be any change. Since once adjacency list is built, you are not bothered about these things. You just look into this list, whatever is there, check them if they are visited. If they are not visited, insert them in the queue. This we will not use, we are working with directed case. I am just putting it as comment. So if it's undirected, you will also write this line. But here we will not use. And next, we will define BFS function. And here we need a starting node, let's call it S. This is the visited vector, exactly of size number of vertices, that is MV. And initialize it with false. Then we push starting node to the queue and while queue is not empty, we will continue. And we will also print it once we pop it. Then we look at all the neighbors of V. What is the way to look at that? So this is the adjacency list. This is the outer vector with a size of 5. And for looking at the neighbor of a given node, let's say I want to look at the neighbor of 3. So we will write adj3, so it will again be a vector. Since we have created vector of vectors, you can also create list of lists. So this is a vector of integers and which holds the value of 2 and 4. You can see here. So we will look at all its neighbors and check if they are visited or not. Neighbors of V, the pop node. So why we are marking it visited right after pushing it? Since some node may still be in the queue, let's say we have inserted 0, then we popped out 0, then we inserted 3 and 1. So 3 and 1 are still in the queue. Then we will pop 3. So 3 is popped, and we insert its neighbors 4 and 2. So 4 and 2 will be pushed here in the queue, and maybe there is a edge from 3 to 1 as well. So 1 is already in the queue. So if just after enqueuing we not mark it as visited, then 1 will be treated as unvisited, and we will again enqueue it. So 1 will come somewhere here. So that's why just when we enqueue it, we also mark it as visited, so that it's not traversed multiple times. So that's it. Now let's build the graph. We have not built it. Graph G, and let's have 5 vertices, the same example that we put here. So in 0 we will add 1, 3, in 1 we will add 2, 0, 1. So we have 5 edges in total. Three, 4, 5. So 0 has 1 and 2, 1 and 2. Then 1 has 2 and 3 has 2, 4. So these are the 5 edges in our graph. Now let's run the BFS G dot BFS, and we want to start BFS from node 0, and let's see what order they are printed. So it's 0, 1, 2, so we missed something. So looks like our graph is not exactly same. It's 2, 2, 2, 0, 1, 0, 2, 0, 1, 0, 3. So here it should be 3 for 0. Let's run it again. Now it's 0, 1, 3, 2, 4. 0, 1, 3, 2, 4. Let's verify. 0, 1, 3, 2, 4. This is our output. 0 is the at first level. 1 and 3 are at second level, or this is at 0th level, this is at level 1, level 2, 3 and 1. So here it's 1 and 3, since we inserted 1 first. Then we have 2 and 4, which is in the last level. So this works as expected. So this you should stick to one convention. Choose one favorite for you. Take vector of vectors, or take list of lists, or a array of vectors. Whatever is your favorite way, stick to it, so that you don't have to think too much while implementing at least these trivial things, and your main focus should be on implementing the algorithm or the problem that you are solving based on graphs. So now let's see the Java implementation. So here let's import a few things. And now we will define the, let's make it graph. So here we are having a list array of lists. So we have an array equal to the size of number of vectors, and each element of the array is a list. since we can add a new neighbor and that will be appended in that list. So this is the adjacency list. Then graph constructor. So we have initialized this outer array of size v, and we have initialized all the elements of that as a linked list. So this is our constructor. Now let's define the same function, add edge. And again, if it's undirected, then we will add madjv. So this function is implemented. Now we had BFS function. S is the starting vertex, and here as a queue we will use linked list. Since linked list you can also insert in the end and remove from beginning. That facility is available, so make sure to do that. If you don't follow that order, if you remove from any other place, then the ordering will change and it will not be BFS. So once we pop it, we also print it so that we know which order the nodes were visited. Then look for all the neighbors of the popped element. And that's all. Now we will create the graph. With 5 nodes. So it's 01324. 01324, same order as C++. Finally write it in Python. So this is the initialization. In the constructor we need number of vertices. So I am following the same variable names and same function names across all the three implementations. So whichever your favorite language of choice, you can follow that. So it's a list where each element is a list. So this creates the adjacency list and the constructor part is done. Next was add edge. And if it's undirected, we will also need to add the same thing. So both are equal. So here we will not use undirected case, we will use directed case. And this is the only change, as I have been repeating again and again. In the traversal part, there will not be any change. So here again we will use a list as a queue. We will insert in the end and remove from beginning. So while queue is not empty, pop it, and from where pop from the beginning. This is very important. Look at all the neighbors of V, the element that we popped. If not visited, push it into the queue, mark it as visited. And we are done. Now we will write the main driver code. So 0 was connected to 1 and 3, then 1 was connected to 2, and then 3 was connected to 2 and 4. And we start BFS from 0. So it prints 01324, 01324. So exactly same order for this graph. So I hope you understood this well. This is very important. You make sure that you are able to not just understand it, but write completely everything in your favorite language. If you are not comfortable, try doing it again and again until you are comfortable with it.